So the question we are doing today is search and 2D matrix. It is the second question of binary search playlist and the 74th question of lead code. So what does the question say? We have 2D matrix. Let's say the matrix is 1, 3, 5, 7, 10, 11, 16, 20 and 23, 30, 34 and 60. Okay, this is the matrix. So in this question it specifically says that the matrix is sorted. That means like each row is sorted, like you can see 1 is 3 is greater than 1, then 5 is greater than 3, then 7 is greater than 5, and the first row of each element is greater than the last row of the previous row. The first element of each row is greater than the last element of the last row. So 23 is greater than 20. Okay, so this is the order basically, 7, then this order, then this order. So now we have to find an element in this matrix. So how do you do it? Let's say we have to find 16. The brute force approach obviously is like keep checking each element 1, 3, 5, 7, 10, 11, 16, 20. Sorry, 16 we found it, so hence it is here. So if there are like 3 rows and 4 columns, so total elements are 12. So to check an element, in the worst case, let's say we have to find 60. So we have to check each element one by one. So we have to do 12 checks. That means for m into n matrix, the worst case m complexity is O of m into n, because we check each element one by one, the full matrix. But obviously it is not a good solution. So let's think of something else. What if we can try binary search on this? As we studied in the previous video, binary search can change the time complexity from On to O of log n. But as we can see, this is basically too many arrays, three arrays inside of one array, not 2D array. So how do we apply binary search? Because for binary search we need one array. We cannot do multiple array same binary search. So how do we do it? So obviously what we will do is there are 3 rows. For each row we will do a loop. For this row, let's apply binary search. So we got, let's say it is m into n matrix. Okay, m rows, m is equal to 3 and n is equal to 4, because there are 4 columns, 1, 2, 3 and 4. Okay, so we do a loop 3 times, m times, and for each loop we have n elements in array. So we apply binary search on this n elements, we get log of n. And then we apply here also same binary search again, starting from here, then the middle, all this that happens. Then we got again log of n, and then for this also log of n. So log of n 3 times, that means log of n m times. So the time complexity is m log n, and space is also 1 as in the previous solution. So this is also same. So this was better than previous one, but still we apply binary search. Let's say there are 1000 rows and 1000 columns. So we apply 1000 times binary search. But binary search, the power of binary search is to like do a lot of numbers in just one binary search, in just one searching function. So why are we doing this again and again? So let's try to find a pattern here. Let me erase this also again. So we know that binary search can be used if the array is like 1D, one dimensional array, we can use the binary search. So why not we assume that this array is 1D array? Because as the question said, it is sorted. That means if we follow this order 1, 3, 5, 7, 1, 3, 5, 7, then 10, 11, 16, 20, then 23, 30, 34, 60, then we can assume it as a 1D array. But the point will be how will we traverse through it, because we need I and j coordinates for each of this value, because we are not given a 1D array, we are given a 2D array. So let's see how we'll do that. Let me give you an example. We will just write the indexes of each element. Okay, we will not write the full element for now, so that you can understand the pattern. So let's say we have a matrix. These are the indices 0, 1, 2. These are indices also. These are the values 0, 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15, 16, 17, 18, 19. Okay, so this is a 4 into 5 matrix. 4 rows, 1, 2, 3, 4 and 5 columns. Let me write the rows and columns also. I am writing this as a 1D array, but actually it is like 4 rows. Okay, 4 rows in a bigger array, so a 2D array. The row is 0, 1, 2, 3 and the column is 0, 1, 2, 3, 4. Okay, so the point is at any point, let's say we are at here and we know that at first row and second column, we have 7. We know this, but how will we find out? Actually we don't know this. We know that we are at 7. How will we find out the row and column for this? Because if we do binary search, what we'll do is low is here, high is here, then somewhere middle is here, then we remove the other part, then the low is high is here, then middle part is here, then again this. But we ought to do this for a 2D array. We have to use it as a 1D array, because like the low and high and mid will be like simple variables, one variable, not two, because for in the 2D matrix we need 2 variables to tell the location of any element. Okay, so if we know the location of the element in a 1D array, let's say this element is the 8th element from the starting. This element is the 8, 9, 10, 11, 12, 13th element from the starting. Okay. So if we have this number, we only know that the current element is 13th from the starting. But how do we know which row and which column it falls on? So for that, what we'll do is simply, let's take this for example. Let's say this for example. So we are at 12 and we know this first, second, third, fourth, fifth, sixth, seventh, eighth. No, actually wait. 12. 12. Third element. Okay, yes, we are good. So we are at 12. Let's take the position as 0 index. Okay, so this is 0th element, this is first element, second element, third element, fourth element, and similarly this is 12th element. So we know that we are at 12th element. Now how do we know which row and which column is this? So simply what we'll do is, for 12, to find the row, the current row of 12, what we need to do is, if we know how many rows we have covered till now, like one row and second row, like 2 rows are done, that means this is the second row, because the first row is 0 and this is first row, this is second row. So for each element, if we can find how many rows we completed, then we can find the row index of this number. So for that, what we'll simply do is, we will just divide it by n. So let's say we have 12. If we divide it by n, n is 4 here. No, n is actually 5 here. Okay. So we get like what is 12? 5 plus 5 plus 2. Okay. If I write it in the form of the numbers. So if we divide it by 5, we get 1 and 2. 2 rows are completed right now, and third row is like pending. So the answer will be like 2. If we divide 12 by 5, it will give us 2. Okay. 12 by 5, 2 point something, 2.4. But in any language, the division means the floor division of this. So we get 2 only. So that means till this point, 2 rows are completed and third row is pending. So we get 2 and the index is also 2 because there is 0 index. Okay. Now we want the column also. We got the row, but we want column also. So how do we get that? Similarly, we did divided by n. Now we will do the modulo n. 12 modulo n is 5. So we get 2. Modulo is nothing but remainder. So 12 is 5 plus 5 plus 2. This is the representation of 12, and the remainder means this number. Like the completed, the full 5 we ignore them, and the incomplete number we take that. So we got 2, and hence we know that this column is also 2. So we can see 0, 1 and 2. So we found out that this is the second row, second column element. And how do we got this? Because at any row, the position of the current element decides, it can be calculated if we know how much pending element is in the current row. Because we see first row completed, second row completed, and third row we have 2 elements completed. That means 1, 2. So this is the third element. But as the indices is 0 based, so we got same value 2. So we got second row and second column. So now we know in a 2D array how can we use it as a 1D array, if we can just flatten it, but not exactly flattening it, and then we just need to like do the binary search now. So what we'll do is, from here on it's very simple. Oh, actually I erased that. 0, 1, 2, 3. Okay. So we have low equal to 0 and high equal to the m into n minus 1, because m into n are total elements, but we do minus 1 because there is 0 also. Okay, like we are doing indices. Low is the lowest index and this is the highest index. So for this 0, 1, 2, 3, 4 and 5 matrix, we have 20 minus 1 equal to 19. 19 is the last index. So now we do simply the like how we did in the earlier question, mid equal to the half of it. 19 by 2 is around 9. Okay, so we are at here. This is the middle element for now. And now let's say we have to find 15. Okay, so we are at 9. This is mid. We have to find 15. This is greater than 9. That means the answer will not lie in this part and this also, because this is not equal. So we have to do is low equal to mid plus 1. So now low is here, high stays here still. Now we do again 10 plus 19 upon 2 for mid. 10 plus 19 is 29 upon 2 is equal to around 19. 29 upon 2. So we got 14. Okay. So now this is the middle element, 14. We have to find 15. We are at 14. That means the answer will not lie in this part. This is the array. We remove the first half. So now this was mid. Now low becomes mid plus 1 again. So now low is here. This is low and this is high. Now we are finally at one array. So the mid will be this one. Now we are 17. We know 15. 17 is greater than 15. That means the answer is not in this part. So now the high is here. Mid, high equal to mid minus 1. So low and high, 15, 16 upon 2. So we got 31 upon 2, which is around 15. Okay. So now the mid is this, and we found it, so we return it. So see how we did this. We converted a 2D array we kept the array same. We did not make a new array, but we treated it as a 1D array. And as we treated it as 1D array, so we found a formula to generate the x and y coordinates of any element in this matrix using just the a single element we have from the starting order. Like we know this is the 11th from the starting. So based on that logic, 11th from starting means second row and first column. We found a formula for that, which is basically percentage n and divided by n. Okay. Now there's a one. Let me tell you the complexity. It was O of log m into n, because m into n total elements, and we do one binary search over the full range of the full elements 0 to 19. So this was the best solution for this, and space is O of n. Now one thing to note is, in this question we were given a fully sorted array, but in some questions we are not. Let me give you an example in which the matrix looks sorted, but it is not exactly. So in this question we were said that each row is sorted and each first element is greater than the last element. This property is what makes it a fully sorted array. But sometimes we are not given this property. For example, let me give you another example which is array sorted but not completely. Let's say 1, 4, 7, 11. Okay, greater than, you can see this row is sorted. Now let's see 2, 5, 8, 12 sorted row again. Now 3, 6, 9, 16 sorted again, we can see. And then let's say 10, 13, 14, 17. So you can see each row is sorted, but now let's check columns. Columns are also sorted 1, 2, 3, 10, 4, 5. But you can see that 2 and 4, this element is in the next row but still smaller than the second element. So we cannot fatten this array completely. Like let's say we cannot assume that this is the order of the 1D array. 1, 4, let me write it, 1, 4, 7, 11, 2, 5, 8. But 2, 5, 8 are less than this. So this is not a good solution. In this question we were given arrays in such a way so that we were able to flatten it into 1D array and assume it like let's say it's just a 1D array, but sometimes it is not so. Okay, so that is for today. Thanks for watching, and I'll see you in the next video.